Okay, so that's a good start with some basic string operations. I have some examples under class examples on the website. Look at chapter 4 and you'll see that I have a whole set of string operations, a program that runs through some string operations, a program that shows you not only the operations we just looked at, but I believe I have an example of not in as well as in. So in addition to the in operator, there is a not in operation that does just the opposite. And you can check these out by going to the documentation for Python. Go to the help section and click on Python docs and go to, you can enter as a search string, and there'll be a selection involving string operations, methods, etc. You can click on any of that to get a whole list of things that you can do with strings, in addition to the ones that we've looked at today. Now, going forward, let's just take a little side trip to talk about the topic of data encryption. We're not going to do a whole lot of this, but it is sort of a fun way to learn or get a better grasp of some of these operations. And of course, nowadays, data encryption, decryption is a really, really important subject, especially with all the commerce done over the web. And of course, as always, governments have all kinds of encrypted files. When they're accessed, they have to be decrypted, and you want to keep many of these files away from prying eyes. But with respect to the web, it's actually quite easy to observe data crossing a network, especially with today's use of wireless networks. The person who is examining this data, often referred to as an attacker, may use, or in all probability is using, some sort of sniffing software. And that's why you never want to, for instance, do any sort of commerce over the web unless you know that the data is encrypted. Otherwise, someone using this sniffing software could quite easily just grab your credit card numbers, PINs, etc. So how do we protect this information? Well, largely we use data encryption to protect the information that we transmit over networks. Now, there are a whole slew of protocols used when we transmit data over the internet. For instance, I'm sure you're all familiar with hypertext transfer protocol. That's how we send web pages across the net. HTTP. When you enter that on to start the URL to go to a web page, that's what that means. It means use HTTP, the hypertext transfer protocol. Well, there's a secure version of that called HTTPS, hypertext transfer protocol secure. Same thing with file transfer. You may send files back and forth, say through some FTP client, file transfer protocol. There's a secure form of that as well. Now, one or more keys are used to encrypt a message when you produce what we call ciphertext. In other words, you want to send something securely, you encrypt it, and the manner of encryption makes use of something called a key. And to decrypt what we call ciphertext, that's encrypted, an encrypted message is ciphertext, we would need the key to decode it back to the original form. Now, when we talk about the original form of a message, we refer to it as plain text. All right, And you'll see this reference made all the time. So we have plain text, all right, and on the other hand, when we encode plain text, we end up with ciphertext. All right, so encoding plain text produces ciphertext. Decoding or decrypting ciphertext produces plain text. Now, there's a couple of examples. Your book discusses both block ciphers and Caesar ciphers. We're not really going to look at block ciphers. That's above and beyond what we need to cover this semester. But we are going to take a look at the simple Caesar cipher. How many of you, when you were small, either had a real decoder ring or saw references to them or used a decoder ring? Basically, the idea of a decoder ring or a decoder tool is one that offsets the characters in the alphabet by a certain distance in order to encode a message. So you would encode each character by moving the character a certain distance, and then you would decode the same character by shifting the direction of the distance and finding the original character. For instance, if I wanted to encode the letter A using the distance +1, A encoded using +1 as a key would give me B. Right? So every letter in the alphabet that I encode using a distance of 1 would simply substitute that character for the next character in the alphabet. A would be encoded as B, B would be encoded as C, etc. On the other hand, if my distance was -1, A would be encoded as Z. Right? So A would be encoded as Z, B would be encoded as A, etc. Here's a little program. You might notice that this program is different from the one in the text. Basically, I looked at the one in the text. I felt that the algorithm he was using was rather confusing, and that perhaps we could explain it more simply this way. The other thing that I noticed was that his algorithm only worked in a positive direction. It didn't work in a negative direction, at least not properly for all letters. So I rewrote it. Here we have an encryption algorithm. Notice that I'm starting with a constant of 26. Why 26? Well, there's 26 letters in the alphabet. So we're going to start with input. Enter a one-word lowercase message. So, we're making this easy. Whenever you see something like this where there's so many limitations, one of the things you want to think about immediately is what sort of enhancements could we place around this basic program to make it work better. Some enhancements that might come to mind are let's make it not just for a single word, make it for multiple words, maybe multiple lines of multiple words, and in fact we might change it so that here the way that this program works, we come in, we can enter a message, it decodes it, it prints it out, but it does it once. And of course now you know all about while loops, for loops, etc., some minor data validation. So you should start, when you examine these simple programs, think about, wow, what could I do with this basic algorithm and change it in a way to have more functionality. So let's look at this example. We're getting our input, enter a one-word lowercase message. Notice the limitations. All right, one word, and it's got to be all in lowercase. Implied here, it has to be alphabetic characters. And then you're going to ask the user, enter the distance value. So what distance away from the original letter do we want to use for the encryption? And here we're going to start with code equals null string. Now, here's something that if you saw this with regard to numeric data, you'd probably recognize it immediately. It's an initialization, right? And with numeric data, say we're adding numeric data, you would expect that before the loop, we would initialize an accumulator, like sum, to 0. Well, in this case, we're going to accumulate characters. And whenever you accumulate characters, or any sort of length of string, you actually initialize your character accumulator to a null string. Right? So that's what is happening right here. This code is assigned the value of null string. Code is our character accumulator. Now we come to the for loop. For character, notice CH stands for character. Again, nothing sacred about the name. It just makes sense as the control variable name when each element will in fact be a character. For character in what? In plain text. Right? So this was the word that was input here. Enter a one-word lowercase message, plain text, and here it is. Now, let's enter the body of the for loop. Notice, by the way, that again, because we're using a for loop, and a string is a sequential type, it will actually march through all the letters. We don't need any indexing here. I mean, we could have done this mathematically if we wanted to get a hold of index 0, 1, 2, 3, whatever. But if we give no range expression here, and instead just give the variable name of the string, a for loop is designed to march through from 0 through the last character in the string, up to but not including the length of the string in the for loop. So it's built in, which is really nice. We don't have to think too hard. So what's the first thing we're going to do? We're getting the ordinal of the character. What does that mean? Well, hopefully you recall from our discussion a week or two ago that if we have a character, an ASCII character, we can see that it has a numeric value. We can access that using the ORD, or ordinal function. And that will give us the numeric representation of the character. For instance, ASCII lower character A is 97, right? And if we were to get the ordinal of lowercase a, it would give us the value 97. ASCII character lowercase z is, when we get the ordinal, is 122. All right, so again, if we were to say ordinal of ASCII character z, we would get the value 122. So first we get the ordinal value of the 0th character, 0 index character in our text. And what are we going to do to encode it? Well, we're just going to add distance to it. So for instance, if the ordinal value were 100 and distance were 5, then the cipher value would be 105. All right. Now, what are the couple things we have to think about here? I mentioned that the ordinal of A is 97 and the ordinal of Z is 122. What happens if when we make this addition, and remember distance could be negative, right? What happens when we make this addition? We come out with a value that either drops off the edge of the alphabet, is greater than 122, all right, or for instance is less than 122. Right? And by the way, since we didn't give the distance any sort of range, we didn't say, oh, make sure that you only enter a distance between 1 and 25. All right? Think about if they enter 0. If they enter 0, then by shifting the letter 0 characters, it's the same letter. The same goes for the value 26. if you were to shift A 26 places over, A plus 26, you would wind up with 123, which is one past the lowercase value for alphabetic characters. And if you cycled back around, it would be A again. All right. So notice we haven't put any limits as to the range of distance. So if our distance is less than 1 or greater than 25, we're going to have to do something about it. So actually, it'll work between 0 and 26. 0 and 26 will just, in fact, give us the same letter. But here, if our value comes out to be greater than z, then we're going to do the sensible thing, which is just to take the new cipher value and subtract 26 from it. All right, so we're going to force it to cycle. We're kind of doing a manual modulus here with characters. Now, notice that this is not an if. While cipher value is greater than ordinal z, it's quite possible that someone might give us some huge number like 527 as our distance, in which case we could cycle around numerous times until we finally come up with a value, the remainder, when 26 is applied. All right, so that's how that works. Now, here we have another while cipher value is less than ordinal a. Let's say they gave us a distance of -5. We could drop off the alphabet on the other edge. And so this would take care of that. We just simply add back alpha count, add back 26 until we came within the proper range. Also notice that I'm not checking, I don't have a while loop that checks both at once. I don't have an if or an else. The two consecutive while loops will do just fine. So if the value is too large, this while will take care of values that are too large. And there's no way that coming out of this while loop we'd wind up with a value that was either still too large or too small. And this while will take care of all too small values just fine. By adding in alpha count, we will wind up with a value that's in the proper range and no longer too small and not too large either. Right? Okay, now here we come to the end of the body of the loop and we come to the bottom, and what do we have? We have our update. Remember I said this is our accumulator, right? And I shouldn't say update. We have our accumulation, right? The update, of course, is done by the for loop since we're in a for. Here we have the character of cipher value. So up here, we change the character into a number. We did all our arithmetic. When we're done, we change the cipher value, which is a numeric value, back into a character. Right? And because this is a character accumulator, we are concatenating it back into code. So initially, code starts with a null string. Here we're saying that code is going to be assigned to the value of the current value of code, which is a null string, concatenated with this new character, right? And notice that we'll go through the for loop for each character in the plain text, perform the same operation, and every time we add in the character, the new character, because we're adding it to the pre-existing code, we're not going to drop any characters. We're going to add the new character to whatever is the current code, which by the end of the loop should contain several characters. And then at the end we'll print the code. Now this program, encrypt2.py, can be found again under the class code link or class examples. Okay, well, encryption is great, but how do we get back to what we had? If you send out a secret message to someone, well, that's all well and good, but now they've got the secret message. How do they get back to the original message you wanted to give them? Well, in order to do that, they need to know what the key is. All right, and for instance, if you encrypted a message by adding distance 5 to each of the characters, in order to decrypt it, they'll have to subtract distance 5 from all of the characters. So I'm not going to go through this program with as much detail, mainly because it's pretty much just like the other one. So in this case, you're going to enter the coded text, right? And you're going to ask the user, enter the distance value used to encode the text. In other words, give me the key. Give me the key that was used to encode the text. And if the key was +5, then to get the new distance, I simply want to take whatever the old distance is and multiply it by -1. And that flips the sign. Right? So if we added 5, we want to subtract 5. If we subtracted 5, we want to add 5 this time. Now our accumulator we'll call plain text, because that is what we want to produce, plain text, not encoded text or code. And here we'll go through a for loop, for character in what? Our code, the coded message. And we're going to do pretty much the same as we did before, right? We're going to get the numeric value of the character. That'll be our ordinal value. Our cipher value will be the ordinal value plus the distance. Remember, we've already flipped the sign, so we're going to do it in the right direction, which is the opposite of what we did before. And then we just pretty much have the same code. While the value is greater than z, we've got to offset it until it's in the correct range. While the value is less than a, we've got to offset it so that it's in the correct range. All right, and basically what you're looking at here is a manual form of doing a character modulus. Finally, we increment, so to speak, our accumulator. We give it our, we take our value that we came up with, and we convert it to a character, and then we add that character to the current value of plain text. Finally, when we exit the for loop, we'll print the plain text, and we can look at it. And again, please download this code, try it out. Here's a quick example of what this looks like. We have, we're invoking encrypt.py. This really, I should have changed this to encrypt2. This is the author invoking his original one. Enter a one-word lowercase message. He enters invaders, enter the distance value 5, and we come up with this, this encoded message, which is just I shifted 5 places, N shifted 5 places, etc. Okay, you can see that easily when we come to the A. 0, 1, 2, 3. A is index 3. So we'll go here, 0, 1, 2, 3. F is index 3. So if we say A plus 5, we get F. Right? And that makes sense. Because when you shift A 5 characters, you get the character F. So now we see the author decrypting the message. Again, this should be decrypt2. Enter the coded text, and we have the NSAFIJWX. Enter the distance value 5. That was the key, remember? Right, so we flip the sign and we get invaders. Our original plain text. Now, these are fun, not too useful today. In ancient times, this still worked. I don't know how people thought this was hard to break, but I guess a long time ago it was. today, of course, maybe not many people were literate in those days. Today, you could break this in moments. Certainly using a modern computer, you could break a Caesar cipher, before you could finish a breath. If you want to know more about this type of encryption and others, take a look at these links, and you might find it interesting.